He's the Joseph C. Tsai Professor of Computer Science at Yale University, where he leads the Efficient Computing Lab. So his research focuses on building efficient and practical computing systems with recent work spanning edge AI, mobile systems, quantum control, and Rust-based operating systems. Before joining Yale in 2020, he was a professor at Rice for over a decade. So Lin, of course, he's no stranger to the MobiSys research community, and he was the recipient of the ACM SIG Mobile Rockstar Award in 2014, and he was recognized for his many contributions to our research community. So his work has received multiple Best Paper awards from top venues including MobiSys, ASPLOS, NDSS, and IEEE QCE. Additional honors include the NSF Career Award, the Test of Time Award, and election as a fellow of both the ACM and IEEE. He's also played a leading role in some major NSF fund initiatives such as the AI Institute for Edge Computing and the Paragon Project for Quantum Control. So today, Professor Zhong will present his team's latest work on rethinking how we serve large language models in robotic systems, where traditional approaches fall short in meeting real-time latency-sensitive demands, and his talk will outline key design principles and a multidisciplinary research agenda for enabling responsive, intelligent robotics. Let's all welcome Lin.
Thank you, Jeremy. That's a nice introduction. You did write it yourself. It's not like I give you my. All right. Anyhow, thank you so much. Thank you all for coming, especially after lunch, and you didn't go to Disneyland and then choose to come for my talk. All right. So nice to be here. I haven't given talk at the MobiSys for a long time. My last MobiSys paper was 2015. After 10 years, I have another one this year, so, and the 10-year drought. Anyhow, but today I want to talk about our recent work, something we started in the past 3 years. How about using large language models for robotic control? And I, as someone who worked on neural networks as an undergrad student, about 30 years ago, I had resisted temptation to work on AI for many, many years, until 3 years ago when GPT-3 showed up. And I figured I couldn't ignore it anymore, so let's do something, all right? But the project that really got me into the robotic control and using large language model is really something about how can you explain your research to your family member? Like your kids ask you, hey, Dad, what you are working on, right? I cannot say massive MIMO or operating system. These things are so far away from their everyday life. One thing I felt, since I have kids, school-age kids, this is a unique American problem, is shooting in schools. And I remember clearly when in some of the morning, I drove my kids to drop them to school. NPR, you heard news about shooting happened in some school. I had to turn off the radio so that my kids don't get scared. So at that moment, I feel like I have to do something, right? As a technologist, as a computer scientist, what can I do? So this kind of urge coincided with GPT-3. And at that time, we started looking to what if people have done in the school safety problem space. So this is a timeline about like different stages what people can do to deal with a school shooting, right? From like days before shooting happened to days after school shooting happened. And what I realized, there is a critical like gap there in terms of like solutions and people working in this space. It's basically 5 minutes before the shooting happened and 5 minutes after shooting happened, right? This is a time window that you can potentially, in the last resort, save lives. We started looking at this problem, and what we found out is 90% of American schools actually have surveillance videos, right? So video everywhere. If you go to front desk, often you will see they have like multiple screen there showing the video, each of camera feeds. But the problem is nobody's watching the video, right? And even and the thing is, when something happen, even if you found something, someone watching the video and found something terrible happen, there's nobody there to intervene, right? It's a public school, under resources, and not many police officers or resource officers you can send to intervene with this shooting incidents. So what we thought about is, why don't we put robots, drones, right? Like every camera, surveillance camera, let's put a tiny drone there. Give a little bit of tear gas, right? Whenever the shooting happens, can we just drive these drones, go tackle the shooter, right? These days with the robot dogs so cheap, right? Unitary robot dogs, $3,000. There are even cheaper ones. We hope they'll become even cheaper in the future. Why don't we just get a few robot dogs in the school, right? Whenever shooting happens, why don't we just some computer program will control the drones and the dogs go tackle the shooter, right? So that's how we started, how large language model could help here. So about the same time, this is 2023, and the people from the robotics community also started to think about using large language model to control robots. And I think everybody basically converged on one solution. It's neurosymbolic approach that you convert robotic control into code writing. Basically, you get large language model to write a program that control the robot to do things. Okay, so and then if you fit into this situation, would be you put some visual encoder like DNNs, CLEEP, YOLO to the object detection in the server. Every school for the video surveillance system, they often have a chip server with a GPU with massive storage there. And you could run this YOLO or CLEEP model there that do object detection, recognition. And then you can then use this information to ask large language model to write the program and then send back to control robots. Okay. We built a system like this, so it's called TypeFly. Basically, use GPT-4 as a programmer. How this works is, in this case, the robots are basically dumb. There's no intelligence in robots at all. They can only move, they have camera, they can take pictures, take a video, and then this image video is sent to the edge server where you use DNNs to basically do object recognition, classification, and to generate a description of the scene, right? So instead of sending image picture to the cloud, we basically generate a text description of the scene. So this is have benefits of being efficient, bandwidth efficient, and also privacy preserving. So because you don't want to send picture, video to the cloud, rather send a text description will basically allay any concern in privacy. And then you basically prompt the large language model to tell large language model, hey, here's what the robot see, and I would like you to do the following things. And then large language model will use the APIs, the skills supported by the robots, and then write the program, you send it back, and then you run on the robots, okay? That's basically starting point. And here, a quick demo of what we have there. Well, in this picture, this drone is really stupid. Just drone can move with camera. And on your left is basically the third-party view, and on the right is drone's first-person view. And the right bottom is basically the dialogue between the drone, the server, and the GPT-4 about general program. So you could ask the drone to find something edible, right? So that's basically the large language model will write the program, which will send to the drone and move it and to search for the room and find objects. And you could include complex logic too, for something edible, if not something to drink, right? So you don't have to, human doesn't need to write anything for the robot. It's basically the ChatGPT is writing the program, okay? Well, but the problem with this, do you think this drone can actually chase or tackle the shooters in a school? It's too slow, right? It's waiting for the ChatGPT to generate a program, then run, then generate another program, then run. So latency is really the problem that between large language model-based robotic control and real-world application. In particular, When the robots run into novel situation I've never seen before, and ChatGPT need to quickly analyze the situation, generate proper reactions in the form of code. And that need to be, if you want your dog to behave like a dog, you need that latency to be below half a second, right? The robot dog need to react within a few 100 millisecond range to be able to appear to be like a dog, to be able to quickly react to novel situation. So that's basically the focus of the rest of the talk, and what we have done to basically cut the latency close to what is necessary. I used to work on energy efficiency, right, for many years. So I realized latency problem kind of like energy efficiency in the way that there's no silver bullet. There's no one source of latency or energy inefficiency you get rid of, then problem solved. Is you find this problem, solve it, then another component become the bottleneck. So today, basically, I walk through a few of these problems and see how we reduce latency. And we'll start with the easy ones, right? So let's briefly talk about how large language model works in the context in robotic control code writing. So large language model is trained to predict next token, right? So you give input token, the model will give you next token, here A. And what it does is append A to the input, and then you predict yet the next one, B. And then you take B and append it to the input again, and so on and so forth, through this autoregressive generation process until you predict end of sequence, then it stops, right? So in a way, large language model is kind of like, it's interesting, it's kind of like a kick a ball, right? You kick the ball, and then you stand there, see the ball rolling, and you lost control of how the ball rolls, and until the ball stops. So that's basically how large language model works, and it's also a fundamental reason why it's slow. So if you look to how typefly work, so this is a prompt. It's actually with a lot of details omitted, right? We started to instruct the ChatGPT, your job is to control the Zhong, and we teach it to program in a particular language, which I'll talk of later, and then you give some examples so that it can learn from through in-context learning, and this is a very long prompt, okay? So if you look at the latency, so this is some data we gathered a year ago. The latency is both input part and output part contribute to latency. And in particular, the latency is proportional to length of prompt and the length of output. And if you look at the data, the output length is actually the determining factor. So long prompt is actually not a big problem these days because the prefill stage is pretty quick. It's output, the token by token generation process, the autoregressive process that's slow. So if you have about 400, for example, tokens, it will take you 15 seconds. So that's basically too long, right? We want this whole thing to go down to hundreds of millisecond level. It's 100 times shorter than that. So we did remeasure the system again a couple months ago, right? So over a year, you can see the latency improve slightly, but still is far away from what we would like to, right? So given this, the first thing you want to do is, can we control robots with as few output tokens as possible, right? What is common practice in the robotics community is use Python as the program language to program the robots, right? And Python is a paragon of human program language. Very verbose, right? It's very easy for human to understand, to learn, but it's a lot of tokens, right? So in this case, the code generated by the large language model, nobody's going to read it, right? Only robots can run it. So therefore, why do we need a super usable programming language like Python? So that's first chip idea is, why don't we design a very tiny language? And the tiny language is super difficult for human to read, like you can see the example there. However, it's just use much fewer tokens, right? So the number of tokens determine the output latency, right? So by reducing the number of tokens, you reduce latency. So we run this, of course, multiple tasks for drones, and you can see about 1/3 of token reduction on average. So that's translated to about 1/3 of reduction in latency, right, in the large language model-based robot control. Okay, the second cheap idea I want to talk about is you don't have to, the robot does not have to wait until the large language model finishes the program, right? So the demo I showed is basically every time the robot have to wait for complete the program from the large language model, GPT-4, before it actually act. The thing is, the robot could start to act as soon as it receives something actionable, right? For example, here's the example, a mini-spec program is basically asks the drone to turn clockwise by 180 degrees and to find if there's any something edible there. If not, then you go to the table, right? So the first actionable statement is turn clockwise 100 degrees. You basically, the robots can start turn around after receiving the first 3 tokens, right? While waiting for the rest to come from. So they're very cheap idea. So therefore, you could do this stream interpretation instead of normal interpretation. Normal interpretation would be you wait, the robots wait to receive the entire program and then starting running it, right? You can see the response time, which is dashed arrow, and the completion time, which is a solid arrow. And then if you use string interpretation, is the robot can start turning as soon as receive turn clockwise 180 degrees. At the same time, keep on receiving the rest of the program and continue to execute. You can see by doing this, we can reduce both response time and completion time. Okay, cheap ideas. And it reduce the response time substantially. So basically, the robots will be 3 times how to calculate. This is a 60% reduction in response time. It's kind of about 3 times faster reaction time. The robots will wait for 1/3 of time before it starts actually acting. Okay. So this is the first bunch of idea, cheap idea, right? So design a new program language for large language model to program. Don't rely on human language because human language is verbose, redundant, use a lot of tokens, right? Let's look at the prompt again, right? This much of the prompt, for example, the green part, is basically teach how GPT-4 how to program, right? It's not specific to any task, not specific to anything when the robots are moving around. Every time you want the GPT-4 to write the program for robots to do something, you will send the green part to GPT-4. It's the same text, same prompt. Only thing changed, these 2 red parts, is the scene description, which is text generated by the DNNs about what objects are in the view and what location, and then there's a brief description of the task you would like the robot to accomplish, right? Every time you're using the GPT-4 to write the program, only the red part change. The rest is the same. So unfortunately, in large language model these days, every time, every prompt is considered a new, stateless, right? You basically recompute the attention states for the green part every time from scratch. So this is how it works, right? So you generate the KV cache, and the KV cache is also known as attention state. It's computed from input token, and that is actually very computation intensive, and it contribute to substantially to the latency to the first token, right? For the first token to show up, the computer KV cache will be most of the latency. And for every prompt, we have to recompute this part again and again. Why can't we share, right? So then they come to our second idea. How can we allow prompt cache? how can we reuse the KV cache, the attention states, for the shared prompt materials between prompts, right? So that for each prompt, you don't have to recompute it again and again. You can reuse previous computed KV cache. So this is a collaboration with my colleague Anurag Kandava and with a collaborator from Google as well. We put on the archive in late 2023 and it showed up at MLSys early 2024. And the key idea is basically instead of the user, the robots, instead of to send prompts, text prompt to large language model, server engine, but rather use simple language called prompt markup language to basically structure the prompt out of a schema. For example, if ordinary use of the large language model, we just send the English text on the left, but we ask the user to basically specify the reusable materials into modules, and the system then will compute the KV cache for the module and save it in the memory. And then later on, when user use the same schema to specify prompts, and the user can indicate what module to be reused. Okay, let me illustrate this. In this here, in this example is, for example, there is a prompt module for the book material, Moby Dick. There's another module for another fiction, White Fan, right? And then there's a module for character analysis. This module basis is they can potentially shared across multiple prompts, and therefore the server engine should save their KV cache in the memory, so that other prompts can just retrieve this KV cache instead of recompute them again. And the prompt module could have parameter, right? This parameter allow you to change the shared text a little bit, and the parameter allowed reuse the field later. The large language server engine will compute the KV cache for the parameter and not reuse it. Okay. So we have the structure called union. So basically allow you could save the precious position ID, which is used to encode the prompt. So basically, in this case, the union basically says the text will either include Moby Dick or White Fan, right? So therefore, when you try to compute the KV cache for these two books materials, you can encode them in the same position ID, right? So because they're never going to appear in the same prompt at the same time. Okay. So with the schema, user basically can define a prompt just like here. For example, schema is on the left, the user prompt would see, the city is Sydney, I'd like to plan a trip, and the parameter is I give a 3-day trip, and I want to highlight the surf spots. So with a prompt like this, only the yellow highlighted fields will be, the KV cache will need to be computed again. Okay. So for the rest of parts, for example, the Sydney planned trip, these are already cached, saved in the memory. Their KV cache can be reused. Okay. So using this trick, we can reduce the time to the by 8 times. So this from multiple seconds, a fraction of a second. So that will combined with the idea we talk about to reduce a lot the total number of output tokens is going to reduce the latency substantially. So here comes the first taste of working on AI, right? Our paper was put in on archive on November 2023. The paper appeared in MLSys in May 2024, and in between, basically, the major large language model service provider basically implemented themselves. So this, compared to what I should talk about this morning, it takes 10 years to deploy something about healthcare. What you get in AI, working on AI is something very new to me. I'm still not getting used to. I don't know whether it's something to celebrate or something to, that means I'm not working on some problem bold enough, right? It's very scary, right? So any idea you have, you put out there is great, quickly adopted, also at the same time saying, if you don't put it out there, maybe someone else would put it out there. So it's pretty scary. Anyhow, so that's the second major trick we have, right? Improve efficiency by eliminating redundancy, right? So therefore, you can cut down the time to first token latency. Now, moving forward, right? So things go so quick, so fast in AI, right? When we started working on this problem, is basically text completion using large language model. Writing code is text completion. In a year, it's become multiple agentic flow, workloads, things like that, right? So basically, allow you to think about, so far we have to think about large language model, writing code sequentially for one robot, right? But imagine if you have 10 robots collaborating, right? And you have to write the code for each robot in this autoregressive process. The latency is going to be super long. So can large language model write a multiple program? Can you parallelize the process of writing code, right? And can large language model actually use tools? When you're writing code, can it use reference manual, look into documentation, look into other people's code base, right? These ideas already showed up in the AI community, right? Using tools, graph of thoughts, using multiple agents like AutoGen from Microsoft. It just suddenly exploded in the past year. That provide opportunity for us to make it to make large language model as robotic control faster, but also point out another problem in today's large language model inference engine design. So the things that matter for latency is I/O actions, right? These days, large language model is no longer simply just text completion, right? As we talk about, the large language model may actually use the web API to search the web, search a document using external tools, right? So if you look at the existing large language model server engine, it works like this, right? Your tool calling logic actually resides on the user side, right? You send a prompt to large language model. Large language model will generate the code that may make a tool calls, right? Call tools, and then then you will need to generate another prompt, and then send the server engine again. Then you receive the response. So that means you are likely to have multiple round trips between the cloud-based, often cloud-based server engine, and the user, which is the robots or the edge server that is driving the robots. So before prompt cache, this is even worse because each time you return from the prompt, the KV cache is invalidated. And then for the new prompt, you have to recompute the KV cache again. With prompt cache, of course, that part will be gone, but the round trip between the user and the large language model server engine is still going to be contributed to latency. So our idea is, can we co-locate the I/O logic with the inference engine to reduce latency? So this is kind of very much inspired by computer system community. Many of you are familiar with Berkeley packet filter, eBPF, right? So basically have some user space logic you put in the kernel so that you don't have to cross the user kernel boundary that much, right? So here's a similar thing. Can we code this logic using some safe language, for example, WebAssembly in our implementation, into something called InfraNet. The InfraNet will basically run on the server engine side and to basically call the I/O actions directly without going back and forth between the user and server. Okay, so very simple idea, and another 15% latency reduction for this agentic workflows, right? Like React is basically reasoning, and ACT is a scheme that about combine reasoning and external I/O use. And code action is basic code using documentation, et cetera, et cetera. And more importantly, we actually improve the throughput by 30%. Our system called Pi, I will explain what Pi means later on. And we compare with the state-of-the-art VLM as a very popular open source large language model server engine. Okay, now talk of three ideas, right? design a new program language just for LLM programmers, right? Improve efficiency by eliminate redundancy, and then co-locate I/O logic inside the inference engine. Now, let's revisit this, right? From a serving prompt, so large language model, so far it's serving prompts. You send the prompt, you can prompts. But with ideas of the co-locating logic with the inference engine, we're moving to serving programs, right? You're not just sending prompt to the large language model. You're actually sending code to the inference engine to run, okay? So this actually provides opportunity to solve many inherent problems with large language problem serving, right? We already talked about the ephemeral KV cache, right? Each prompt, basically the KV cache is invalidated, so therefore you cannot reuse. We have to shoehorn solution, use a prompt cache, right, to solve this problem. And this is uncontrollable generation, right? So I had that metaphor, large language servings kind of kick a soccer ball. You kick it, and then you don't do anything, just wait for the ball to stop. That's basically large language model. And we, computer scientists would like to, can we do something? Can we actually control how the ball rolls? Can we decide when the ball stops, which path the ball will take, right? So we would like to change that too. And another thing we already talked about these days, all these fancy optimization to agentic use of large language model have a lot of the optimization, basically, they have to run on the user side, right? Therefore, require a lot of interaction between the server and user, leading latency. And also make, if this is the model of the business is, if the service provider, they consider some optimization as important, they will implement in their engine, and then they may help you solve some problem. But the things that become the optimization very difficult to combine and choose and pick, right? You either have to implement or not. So if we look back to prompt cache have already differed from this autoregressive generation by allow you to have programmable control of the KV states, the KV cache, right? So prompt cache basically says, right, I could, using the schema, to dictate which KV cache will not be invalidated, will reside in memory. And for a new prompt serving, where that KV cache state will come from. You don't have to compute it, you can just take it from the cache, right? So it's can't, but the problem with our current implementation prompt cache is the inference engine have to implement. So that's why like we are happy and also scared, like Anthropic and Google, OpenAI, they modify their server engine to provide this API for people to use prompt cache, right? But other than that, you as a user, you have no control. You have to rely on the service provider to provide this stuff. Now, with the idea from co-locating I/O logic in the engine, right? Have some user code running inside the inference engine. We can potentially implement prompt cache as a server-side logic, right? The only thing we need is the inference engine provide API for KV cache management. And the prompt cache just simply become a simple logic infernet, a prompt cache infernet that include in your prompt, which will use the API to decide where the KV cache value come from, okay? So now, if we take this approach, the prompt cache will become like this, right? On the left, that's a schema, which is a primitive programming language and have to be supported by the serving engine. To something on the right, basically is a WebAssembly type of a program that doesn't only need the service engine to expose certain APIs and doesn't require the server engine to actually implement the prompt cache itself, okay? So in this way, we're changing the large language models serving from prompt to program, okay? This is good news for computer science major, which I'll talk about later. Now, to push this scheme further, that we need two things, right? We need a user-supplied program, infernet logic, Number two, the inference engine need to provide API for inference control, right? With these two, then basically we have something we call software-defined generation. Right now, the large language model there's no software control. You kick the ball rolls, stop. And software-defined generation basically says the user provides a program that based on the API provides inference engine, I can precisely control how the ball rolls. Okay. And with software-defined generation, we basically can convert the prompt serving large language model use into program serving. And we can change ephemeral KV cache into reusable, selectable KV cache. We could precisely control the generation. We can determine how a generated token is interpreted. For example, you generate token A, it could be a function call. The A could be anything, right? We in software define what the token A will be used and how the A will be used. Instead of appended to the input, we could decide to, it's just token, we analyze it, we throw it out. Or we can even append this token to another generation process input, right? So to provide this flexibility for you to do all this weird stuff. And of course, by having this logic on the server side, we'll be able to incorporate user-defined optimization into the server engine, make the innovation faster, and also get rid of the round trips between user and server ends. So this is, again, goes back to this picture. This is a fixed autoregressive loop for prompt serving. So this is what we see today's LM serving, right? Autoregressive. And inside it is basically you have a prompt come in, there's a batch stage, and then you embed the tokens, the prompts, and you prefill, which is you generate the KV cache, and then you decode, which basically is LM, as a neural network, take the KV cache, predict the next token, and sampling basically is look to all the possibility distribution, probability distribution of possible token and take one. Okay, this is the current internal working of large language model inference engine. What we propose is something called programmable inference engine, PI, that's where the name PIE come from, is in which we take this pipeline, we chopped up into different pieces, right? Each piece become API handler. And then with the API, the user can basically write the program, decide the sequence order and what API to call, okay? With that, with this design, this autoregressive inference process is simply one possible of the millions of possible programs you can write. For example, I showed on the left is the program that actually implement autoregressive generation on top of Pi. All right, here's the good news, right? When GPT-3 showed up, our first reaction is English major, they're screwed, right? Because we don't need English major, we could just ChatGPT can write. And later on, we realized we are screwed, right? Because now English major can't write programs, right? They can just dump English to ChatGPT, ChatGPT give you a program. So we'll lose our job. Now, with software-defined generation, look, we still need to write a program. And this program is a program language in the paradigm. There's not enough training data yet there. So that means computer science major will still have some years to be the human that produce training data for large language model to learn how to write program for software-defined generation. Okay, so for now, our job is safe. Victor, you don't believe this. You think we're screwed anyway. All right, we started with school safety to latency reduction, and we went to software-defined generation and to SDGs, safe computer science majors. I think, let's get back to latency. I think time sensitivity is the key for robotics, in particular to passing something called embodied Turing test, right? We are familiar with Turing test. It's basically based on dialogue with, you can tell if your partner is AI or not, right? So in the the robotics and also neuroscience community, people have to say, hey, in conversation, right? Not language, but also a lot of other things. So this is called embodied twin test. So for embodied twin test for robots, if we're building robot dog, is really wanted the robot dog to behave like a dog, right? So therefore, latency is super important. These days, I think we can build a very convincing robotic sloth or tortoise, right? But for a dog, for a cat, for a human being, I think our latency is not there, right? For us, for robots to pass embodied twin test for a dog or cat, we need to further reduce the large language inference latency. So I challenged a student who, like Guojun, who did the drone stuff, to say, hey, why don't you make your robot dog look like a dog with all the tricks we have together? So Guojun showed me this. He recorded yesterday. So it's a unitary dog, and he holding the ball. So latency matters. If you move forward, the dogs cannot move forward quick enough, right? So by the way, so all the intelligence part for the dog is actually large language model writing code instantly using all the stuff we talk about, right? So this is way much better than the drone I showed at the beginning, but still far away from chasing the active shooter in a school. Okay. All right. So another insight is actually when I read the article about the embodied twin test article there, my reaction is robots do not need human level intelligence, right? If we run the robot dog in the school to chase off shooters, we don't need the super smart large language model. And also robots do not need to think in human language. Right now, the large language model are trained and to think in human language, either program language or natural language. And what we already taste from Python, right? Human languages are verbose, redundant, a lot of token, and even worse, were ambiguous, irregular, right? Unconstrained, of course, very expressive, right? Which lead to hallucination and the weirdest thoughts, right? Can we design a language just for robot dog to think? For robot dog to think fast, right? So the inspiration comes from the fiction 1984, right? How many of you have read this? There's an appendix of this language, of this book, about a new language called Newspeak, right? What Newspeak is a language in which you cannot think about anything that anti-government, right? So basically, example of restricting vocabulary and grammar expression. So design a very restricted language, a small language, and train a model to help the robotic dog think. We don't need super large language model. We do not need to train the language model with all the human English materials or language material out there. So of course, there are people have already thought about this, right? The language, not to train the model to control robots. There's something called control natural language, right? The basic English only have 850 words, very simple grammar. And also the aviation industry, right? Airplanes have technical manuals. They have something called simplified technical English, which avoid all the ambiguity and irregularity of English. And then there are construct language, right? Like this Tokipona is a tiny language designed by human, rarely used by any human. Maybe it's time to use them to train robots, right? To train models to control robots. Let robots use the language. I think here's maybe the time to conclude my talk. I think for time sensitivity, reducing latency, there is no silver bullets. There's a lot of tricks we could use, but I think right now, even with all the work we worked on, I think we're still 2x away from a latency. We really want the robot dog to behave like a dog, right? To think fast, react fast as a dog. Part of the challenge comes from large language serving, which we talk a lot about today, but there also challenge come from design actuators. Actually, the motors, high quality motor that can react fast is actually very expensive. and it's very difficult to make small. If you want a tiny dog, tiny cat, to be agile and fast running, fast reaction, is actually today we still have to wait for the motor to get there. I think moving forward, I'm really excited by the two ideas basically was leading to one software-defined generation that are going to completely change how large language model is served, and build small models for small language and use these models to control robots and with low latency. Okay, thank you. That's my talk. Thank you for your attention.
All right, thanks, Lin. So I think we have time for a few questions. The microphone right there.
Okay. Thank you, Professor, for the very interesting talk. And this is Leming from Hong Kong PolyU, and I have a question regarding the prompt cache. So it seems that you design a new prompt language to represent those redundant prompts. And my question is that since we have many different tasks and different scenarios for LLMs, so do we need to design different prompt templates for the fast serving?
I think right now that's how the industry implemented, right? They allow you to define templates, right? And then use these templates to support prompt cache. But I think the right way to do it actually use software-defined generation. Therefore, you just write a program, right? So you allow you to, your templates basically become part of template. But you don't need a separate template to implement the prompt cache.
Okay, and then I have another concern. So even if we can program the prompts, the structure is still very diverse. So the KV cache still need to recompute it.
Okay, so let me try to rephrase your question. Your question is because the prompt can be very, have all kinds of different forms to reuse. So the current way of reuse is basically you have reuse based on template,
yeah,
right? So which is a schema, right, in our work. That's true. So basically for any reuse case, you have to define a schema. You have to anticipate this is a kind of a reusable segment, right? Therefore, I use schema or template to instruct server engine to cache that part, right? So that's how it works today. Yeah, so you have to, for each reuse case, you have to define your own template.
Okay. I see. Thank you very much.
Hi, Professor Lin Zhong. I'm Xiangliang Chen from Carnegie Mellon. I really like your talk. In your presentation earlier, you mentioned you designed a new language for LLM to generate. I've noticed the language itself is very not human readable. It's pretty dense. I think that's probably used for efficiency whenever it comes into the streaming. That's a really smart design, but also I was wondering, since it is LLM generated code, so it could possibly it's not correct. So how do you make sure the semantics of the mission that your LLM generated is correct? How do you validate that, given that the generated code is not even human readable?
That's a very good question, right? So, and I have to say that's actually a very important direction by itself, right? The people work on formal methods, self-verification, they have working hard at the problem, right? But my point is, we could also design a language that's more amenable to formal verification too, right? Instead of Python, instead of have huge semantics, we could define a small language with small semantics, therefore it's easier to verify, right? So, I think in the end, the semantic correctness depends on the real action of robots, right?
Yeah.
So I think formal verification can only verify certain property, right? For example, whether the robots will ever hit something, right? That's something you can reason using the code and using the current state of robots, right? So I think that's a very important direction to formally verify certain property of the large language generated code. And the opportunity here is we don't need get large language model to write human readable code. It can be code that can be understandable by the form correction tool, right?
Thank you.
Okay.
Hi, Lane. It was a good talk. Really enjoyed it. So my question is actually similar to the one that he just asked, but I want to just pop one level up and sort of think about the scenario that you were trying to do. So I have 2 points here. One is you just kind of mentioned it, but didn't say much about hallucination or reasoning problems that LLMs have. And the one related to that is LLM the right solution for this problem anyways? Like, why are you going down that path when you could pretty much solve or do this problem by just using the traditional classical vision technologies and then sort of try to do the same thing? But why? So given the problem with LLMs and the fundamental issues with them, why would you go down this path? And
Okay,
given
I
the
think
latency
there
issue?
are 2 points. You said traditional tools are enough, computer vision tools are enough. I think the computer vision tools are enough to understand the scene, to generate the description of what's happening there, right, in the view, which we leverage. But there's no conventional technology that actually could write code for the robots do a job. So today, how it works, a human write the code. You write the code for the dog to dance, write the code for the dog to do some tricks. But in a low-vol situation, there is a shooter showed up, you want the dog to follow that shooter, which could be any low-vol situation. Large language model, I believe, is the hope that you could instantly write the code based on the low-vol situation, based on current state of the world, and do the job. And to get back to hallucination, number one, I think that's a problem the large language model NLP community is working on. I'm not expert in NLP. I have been talking about the server engine, not the model itself. So they're working on it. Number two, I believe the direction we talk about using a highly restricted language, use a small language, and also using software to control the generation process, make sure the generated token, the output is short, right, is actually help allay some of the concern about hallucination. I think the problem of hallucination is solvable. There are techniques to deal with that.
Okay, I don't want to take too much time because there are a lot of questions, but my counterpoint to what you were saying is that you are punting on the reasoning, the incorrect reasoning that can happen or the hallucination in a situation where you're expecting the system to actually do the right thing when following the thing. And I don't think without a human in the loop, you can actually do the right thing. You cannot allow the system to just go by itself to follow the shooter. And that's the reason why I sort of said the traditional approaches might actually be better, because there you can at least reason and you can constrain the problem for the robot to do only certain things rather than open it up for it to do
Two points to your question. One is I agree with you. If any problem traditional tools can solve, we should not use large language model, right? Number two, I think in academia, we need to dream big, right? We need to think extreme situation, right? No human in the loop. But if I have to do a startup, deploy products, probably there will be human get involved in the loop, right? So like the robot taxis these days, there will be one human drivers behind like 5 or 10 cars out there. I've imagined for this, the first time you deploy in school, perhaps it will be one officer that control robots from 10 schools, something like that. Okay, all right.
Okay, I think we have time for one more question.
Hello, Professor.
Let it go? Okay.
I'm Hao Wen from Tsinghua University, and I'm advised by Professor Yunxin Liu. And we are also trying to develop some programming language that is suitable for both large language models and humans. And so I'm very interested in your first programming language work. And I say that you do a lot of things for the work so that you can reduce the token consumption and something else. But I'm wondering whether the performance of this programming language is the same with Python, because intuitively, so So the large language model is pre-trained on large scale of Python code, but you only define this new language in your prompt, almost like you are using prompt engineering to make it as well as the large scale training data. So I'm wondering whether this can work.
Empirically, it worked. So the language is not that different from Python. It's a small subset of Python. Syntax-wise, it's much smaller than Python, right? You can look the code example, right? So, but inherently, it's still very much similar to Python. So from our experience, we have not observed that like the large language model have higher chance of make error using minispec compared to Python. Actually, by reducing the number of output token, the length of program, actually we improve the chance of a generated program being correct. So the concern that the minispec, the novel language, like the large language model has not been trained with, we start with that concern, but empirically, it just didn't show up. Okay.
Yeah.
I don't know why. That's about working with large language model. You don't know why it works. Okay.
Thank you very much.
All right, thank you for your questions.
All right, so we have a coffee break until 3:15, and